Hello everyone. Today I am going to present my MSc thesis titled Settling Behavior of Non-Spherical Microplastics in Turbulent Open Channel Flow, supervised by Dr. A.T.M. Hassan Jubair sir. So, firstly, we'll go through the background of the study, then the objective and methodologies, and lastly, the results discussions and the references. So, the background of the study, the global production and consumption of plastics have increased exponentially in the past few decades. From the graph in the right-hand side, we can see that if the current trend of plastic production continues, then by the end of 2050, the total amount of produced plastics will cross well over 1,000 million tons, and most of these plastics have been discarded. Because of the improper disposal practices, these discarded practices have resulted in serious consequences for marine ecosystems. In this figure, we can see the plastic pollution in a marine ecosystem where the plastics have been gathered in the shoreline. Over time, large plastic debris breaks down through physical, chemical, and biological processes into particles that are less than 5 millimeters. These particles are commonly known as microplastics. In the figure, we can see that the various physical, chemical, and biological processes by which the larger plastics are being converted into the smaller ones. Microplastics have now infiltrated nearly every part of the marine environment. In the figure, we can see that we have found microplastics in the sea ice cap of the polar regions, in the sea surface, and even in the deep water columns and the seabed. Rivers play a crucial role in transporting microplastics through larger water bodies like oceans and lakes. After releasing these particles, microplastic particles, they are generally dispersed in the water, and after a amount of horizontal dispersion, they begin to settle down. After settling at the bottom, they are again resuspended in some cases, or they remain there for their entirety. However, the governing mechanism of microplastic transport, including their deposition, accumulation, and transport, remain poorly understood. So, why do we need to learn about the settling velocity? Because it determines the residence time, that is how much time the particle will reside in the atmosphere, in the oceanic atmosphere. Their deposition behavior, that is how will they be deposited, how much amount distance will they travel before depositing to the bottom, their transport distance, that is how much distance they will travel, and lastly the duration of exposure for aquatic organisms, because during these times generally the aquatic organisms or the fishes, they generally take up microplastics along their food. So now there are many physical properties which influence the settling velocity of microplastics. From literature, we found that physical properties such as density, size, and shape are the main factors which determine the settling velocity of microplastics. Besides this, turbulence also play an important role. From what we have found, most experiments regarding the settling velocity of microplastics have been conducted in quiescent water. One of the studies, Ijaz and the other authors have investigated the settling velocity of spherical microplastics in turbulent flow conditions. However, the settling behavior of non-circular microplastics under turbulent flow conditions is yet to be explored. Now comes the objective of the study. There are 4 objectives. The first one is to conduct laboratory experiments to obtain settling trajectory of non-circular microplastics with various density, shapes, and size in quiescent and turbulent flow condition using image and video analysis. The second is to analyze the settling trajectory and calculate the instantaneous velocity in streamways and vertical directions of the microplastics based on experimental dataset. To investigate the interaction of microplastic with the surrounding flow dynamics, and lastly, to study the effect of density, shape, and size on the settling behavior of microplastics across different flow conditions. Now, I'm going to state the methodology of my thesis. Firstly, we will be using 2 types of materials. The first one is PETG, that is polyethylene tetraphthalate glycol, which is commonly used for the production of plastic water bottles. And the second one is PLA plus, which is polyacetic acid used for mainly producing the food grade containers. I have decided to use these two different plastics because these are the most used one-time plastics that we use in everyday basis. For the size and shape considerations, we will be using dimensions ranging from 2 millimeter to 5 millimeters, and we will be using 6 different shapes. The shapes are as shown here. There will be 4 angular shapes that are the cube, rectangular prism, square plate, and square prism, and there will be 2 circular shapes, which will be circular cylinder and the circular disc. And here is the actual sample of the microplastics that I have used for the experiment. In the top part, we can see that the cube, square plates, the circular cylinder, and in the bottom, we can see that the rectangular prism, the square prism, and the circular disc. All of these have dimensions ranging from 2 millimeter to 5 millimeter. And we'll be considering the settling velocity across 3 different scenarios. In first case, the flowing water speed will be 0.1 meter per second, the second case 0.2, and the last case 0.3 meter per second. So now we will be going how I conducted the experiments in the quiescent water. In the figure in the right hand side shows a description how shows the experimental setup. So we can see that a plexiglass column with a cross section of 30 centimeter into 30 centimeter, and the total height of the water column was 150 centimeter. There is a black background which contains a checkerboard pattern which will help us to track the particles. A Panasonic HC PV100 camera was used. The recording resolution was full HD, that is 1920 into 1080 pixels with 50 frames per second. The camera was calibrated with a ruler placed at the center of the column, which will be used for tracking the particle positions. The observational area was set 70 centimeter from and to 40 centimeter below from the column bottom. This is the actual observation area. This has been selected on a trial basis where we found that the microplastic particle had already reached the settling velocity. The particles were pre-soaked 3 hours to reduce the static charge effects and also introduced 2 centimeter below the water surface to minimize the surface tension. And when conducting the experiments in the turbulent water, we used our large recirculating open channel flume measuring 21.34 meters in length and with a cross-sectional area of 0.76 into 0.76 meter. And the longitudinal slope was maintained at 0.3%. The water velocity was measured using an ADV. A constant water depth of 0.45 meter was maintained, controlling the tailgate in all flow conditions, and a dual camera setup was used for recording the particle motion. Camera calibration was done using another checkerboard pattern which was placed along the flume center line. Here is an schematic diagram of the experimental setup of the pinch channel flume. Here is our recording section, and in this funnel we actually place those microplastics through which the water carried it downstream, and we also set up a mesh at the downstream to collect the microplastic particles. Here is an actual observational area, and here is our dual camera setup, one at the side of the flume and another one at the top of the flume, and the a funnel was used for placing the microplastics in the water. Now, the results and the discussions. For here in this figure, we can see that the measured settling velocity of the microplastic particles in the quiescent water. The blue column shows the PETG particles and the orange column shows the PLA plus particles. From what we have already known that PETG has a slight higher density than the PLA particles. So in all cases, we found that the settling velocity of the PETG microplastics were a little bit higher than that of the PLA ones. And also we can see that for each of the shape, the increase in size, like say for the cube, the smallest cube, which is of 3 millimeter, have the lowest settling velocity, and the cube, which is the largest one, that is the 5 millimeter cube, have the highest settling velocity. This observation can be seen across all the 6 shapes. Now, for further for further calculations, we will be developing some dimensionless parameters. There are three dimensionless parameters: the dimensionless particle diameter d star, the particle Reynolds number REP, and the diameter of a volume equivalent particle. All these formulas have been used for calculating these dimensionless parameters. Using these dimensionless parameters, we can develop the relationship between the dimensionless particle diameter and the particle Reynolds number for quiescent water conditions. From our figure, we can see that a positive correlation has been achieved, and the value of R square was determined to be 0.902, and also the actual values have a good clustering from what we can see in the figure. The equation we got that was the Reynolds particle number REP was equal to 0.83 into d star to the power 1.55. Rearranging this equation, we can use this to predict the settling velocity of the microplastic using the equation omega sp, which is the predicted settling velocity of microplastic, which is equal to 0.83 nu into d star to the power 1.55 divided by dn. To assess how good is our predictive model, we will be using two statistical parameter, the mean absolute error and the root mean square error. Using these two formulas, we found that the performance of our microplastic predictive model was a good one, which gives a mean absolute error of 7.44% and RMSE of 9.04%. Also, we found that both the predicted values have been clustered along the positive and negative side of the perfect correlation line, giving us a rather good predictive model. Now, we are going to compare the settling trajectory of microplastics. Firstly, we will compare the settling trajectory of the cubes. So, this is the figure showing the settling trajectory when the flow velocity is 0.1 meter per second. So, we can see that the particle, which is the smallest one, that is 3 centimeter cube, have traveled the mass distance, and the 5 centimeter cube have traveled the least distance. So when we increase the flow velocity to 0.2 meter per second, we found that the amount of distance traveled horizontally have greatly increased. We also found that the trajectory is shown to be greatly oblique in nature. This is because of the fact that due to the angular nature of the cubes, the flow is actually diverting the cube from its ideal trajectory. That's why, and since the particles are of angular nature, this oblique trajectory is seen to be much in this case. So in case of square plate, we also see the same thing, that is the square plate having of the smallest size, that is 4 centimeter into 4 centimeter into 3 centimeter, have traveled the furthest distance, and the biggest square plate microplastic have traveled the least distance. And in case of increasing the flow velocity, the distance traveled along the flow have greatly increased. In case of rectangular, this is the results for the rectangular prism in case of 0.1 meter per second and 0.2 meter per second. And lastly, this is the result of the square prism in 0.1 and 0.2 meter per second. So we found that the square prisms of particles in 0.2 meter per second were the cases where it traveled the most distance along the angular particles. Now, in case of the circular particles, so we will be going through first the circular disk. One key difference we saw from the circular particles from that of the angular particles is that the trajectory of the particles have been clustered around a single line much more than that compared to that we saw in case of the angular particles. And also there is a little less oblique in this case compared to the angular particles. This is the results of the circular cylinder, and in this case, when the flow velocity is have been increased from 0.1 to 0.2 meter per second, the amount of distance horizontally covered had been increased greatly. Now we are going to compare the time average streamwise velocity profile of the microplastics. So in this case, we found that there are actually 3 phases. the initial adjustment phase, the transitional phase, and the terminal phases. And the dotted line is actually our water velocity profile, and the dots of different colors and different shapes are the actual microplastic velocities. And in the initial adjustment phase, we found that the velocity of the microplastics is actually greater than the flow velocity. And then as we go down the bottom, in the transitional phase, the velocity is actually more aligned with the water. And as we go towards the last phase, in the terminal phase, the particles have a good amount of lag in their velocity, which we have seen. And for cube particle, this amount of lag or the variation of their velocity from the actual water velocity have been recorded the highest. This is the result for the square plate. Similarly, what we found in case of the cube, this result still persists here. This is the results from the rectangular prism. This is for the square prism, this is for the circular disc, and this is for the circular cylinders. What we found that in case of the circulars, the amount of difference or amount of lags or deviations of velocity from the water velocity is actually lowest compared to the angular ones. Now we will be talking about the time average vertical velocity profile. In this case, the dotted line is actually the settling velocity of the microplastic in the still water, and the dotted and the dots of different colors are actually the vertical time average vertical velocity. What we have seen that in the initial adjustment phase here, also the vertical velocity is greater than that of the velocity in the still water, and during the transitional phase, the velocity tries to match itself, and in the terminal phase, there is a significant velocity lag between the settling velocity of microplastics in the still water compared with the turbulent water. This is the case of the cubes. This is the case of the square plate. This is the case of the rectangular prism, square plate. These are all the results from the circular disc, and these are all the results from circular cylinders. Now, to summarize all the results, we found that the microplastic particles tend to settle with their broadest face, which is the largest projected area normal to the line of the predominant line of motion. We found that the smaller and lighter microplastic particles travel further along the flow direction than the larger and heavier ones. The angular and flatter microplastics takes much longer to settle compared to the rounder ones, and thus poses a larger duration of exposure for the aquatic organism. And these are actually the particles which have been found most in various aquatic organisms like fish. The time average streamwise velocity of microplastics is generally greater than the flow velocity in the initial adjustment phase. This later decreases and becomes closer to the flow velocity in the transitional and terminal phases. The mean reduction is noticed ranging from 2% to 17% in all cases. And the velocity lag in the streamwise direction is actually due to the particle inertia and increases as the particle size or the density increases in the open channel flow. The time average vertical velocity of microplastics is generally greater than the settling velocity of microplastics in still water in the initial adjustment phase. This later decreases and becomes closest to the settling velocity in the still water in the transitional and terminal phases. The mean reduction is noticed ranging from 2% to 5% in all the cases. The reduction is generally referred to as the loitering effect, which indicates the upward force experienced by the microplastic particles due to the relative motion between the microplastic and the fluid, which actually causes the lag of the particles. Here are all the references that have been used. Thank you for your patient hearing.